Okay, today's topic, intro to the next lesson, is called logistic functions. What? What did you say, Mr. Brigham? Logistic functions are a different type of function we're going to look at. They don't fit in the normal classes we've talked about so far. Our lines, quadratics, exponentials, power, and logarithmic functions. Logistics are going to be something else. And Charlie, just remember, you can get the limo out front, take the limo out front, and you can get your shoes in every style and every color. What does that have to do with the problem? Well, let's take a look. Let's say I had a big, giant field and I subdivided to build houses on it. I'm going to sell my houses. Oop, I put the big house right there. Charlie, you get to live in the big house. There's Charlie. He's in the big house. And what I just start to do is I start to sell these properties. Well, when they first start to sell, the number of houses sold starts going pretty fast because there's a lot of houses to sell. So the number of houses selling initially are really fast. But after time goes by, there's not a lot of properties left. So the number of sales still keep increasing, but that rate they increase starts to slow down. And eventually, there's a maximum number of houses I can sell because I'm out of pieces of property. So what I have is I have an example of some home sales at month X and how many houses have sold up to that date. And you can see these numbers are always increasing. But at first, after 2 months, you can see it got to 103 already. But 2 months later, it's only up to 117. And so the rate of increase starts to slow down. So what happens with a logistic function is first it starts out like an exponential function, the first half of it. And then it grows really fast. But then about halfway through, it's still growing, but the rate of growth starts to slow down. It kind of looks like a logistic function. Looks like a log function. Oh, did I write logistic down there? That could be a creamer dollar, Charlie. Yeah, Charlie, you got me. That's a creamer dollar, Charlie. I should have written logarithmic. Logarithmic function. So what happens is, we have this function, and there's a maximum, the C value right there. We have this type of function that starts out with an increased growth, a quick growth, and that growth keeps happening, but it slows down until it reaches a maximum point. And this is known as a logistic function. That's an I. Because the function is the best of an exponential and the best of a logarithmic. So it's the best of both worlds. It allows you this massive growth, but it allows that growth to slow down and stop. And this is true of a lot of things in nature follow this pattern. Virus outbreaks, things for sale, things like that, which we're going to look at problems coming up. The general equation for a logistic function looks like this. That's the general equation. C equals 1 plus AB to the negative x. And there's another one that's used sometimes. We're not going to use it right now, which is AE B, A to the negative BX, which we're not going to use. It just allows E to be involved in the problem. So sometimes you'll see it, though. We'll focus on this one right now. This is the format for what the problem looks like. And you only need to know what's in the green box. In general, a logistic function is an exponential on the top of a function and some other exponential on the bottom of a function. And they counteract each other because as this gets bigger, the bottom of the fraction also gets bigger. So what it does is it forms that increase and that flat out shape. And we'll talk about that more in the next class. But the big key here is this is our general equation. But this time, you'll notice in the past we had two variables, A and B. This time we have A, B, and a new variable, C. Oh, are we going to solve for three variables? No, we're not going to have to solve for three variables. C is an easy one. It is the maximum population of your function, either the maximum at the start or the maximum at the end, wherever that happens. So, for example, if I'm going to do, let me just scroll back for a second. If I'm going to look at this initial function right here, if I want to find a particular solution for this equation, I'll use a first point and a last point. But I know, because I've already checked, that the maximum number of houses, whoops, what just happened there? wrote that number on there. I only had 100 and someone wrote 1,000 on there. I don't know how it got there. Let's erase that. I know the maximum number of lots I had. I have a pretty big field there. It's 170. So that maximum number goes on top. That's the max. And then in class, we'll look at how I do what we've done so far in the other lessons, which is I found a particular x and y and filled them in twice. We'll talk next time about how we solve those types of problems. And lastly, here's an example of what one of those functions look like. The maximum occurs at C, and it's not a turning point. It's called a POI. It's called a point of inflection. It's where the concavity of the graph changes. So the graph here is happy to that point, and then after that the graph is sad. And what that means is, it means the graph is still increasing, but here the rate of increase is increasing, if that makes any sense. It keeps going up and up and up at a faster and faster rate. If I want to look at that, I'll draw these little tangent lines on here. They look like the slope of the graph, and you can see the slope is getting bigger and bigger and bigger, where on this part of the graph the slope is getting smaller and smaller and smaller. So whatever we reviewed here, I know I only have 30 seconds left. We talked about a new type of function called a logistic function. It's a special one. You use it when you have something that can grow fast, but that has to slow down because of size. The general equation is this one right here, and that C is always the maximum population, and the POI, the turning point, occurs halfway through at C over 2. I will see you on Monday.